Hello, welcome back. This is Calculus by Dr. Oz. In this video, we're going to go through a wonderful application of differentiation. So far, we learned a lot about continuity and differentiability of functions. So now it's time to bring all of those pieces together and to have a list of guidelines to be able to accurately analyze and sketch graphs of functions. And for that reason, we have only one learning objective to achieve today. It's analyzing and sketching the graphs of functions. The truth is that once the expression of a function is provided to you, you can go ahead and simply punch that in to a graphing utility, and that could be a calculator or a software. But you will realize that there is no way to graph the entire function. So the decision is up to you. What part of the graph is the most crucial that you should tell the graphing utility to show that part of the graph to you? So how do you analyze that? How do you figure this out? Let me show you an awesome example just for you to see why what part of the graph to show is very crucial. So we have a cubic function here, and you simply go ahead and punch that into your calculator, and depending on what x min, x max you're going to pick, the graph is going to change completely. So in the first graphical output, you see that x min is -2, x max is 5, and y min is -10, and y max is 40. So you can see some portion of the graph, but not the full picture, because if you expand the x interval so that you have x min to be -10, x max to be 30, you see the other portion of the graph over there, because in the first graph it looks like the graph just increases all the way to a certain point, and then it makes a peak, and then it goes down, and it looks like from the graph that it just goes to -infinity, right, as x increases. But in fact it's not, because after a certain point it makes a turn, as you see, and then after that turn it goes back up. So if you just look at the first graph, you won't be able to see this behavior. Because you have a hill and you have a valley. So, and then in the first graph, you can't see that there's a valley over there. Now here is the important question. Is this the final graph that you should make an analysis for? Do we need a third viewing window to be able to see the full behavior? So to be able to answer that question, you got to use the tools of calculus. All right, now let's talk about the guidelines to determine a good viewing window for a function in your calculator or whatever the graphing utility you are using. So the first item is all about pre-calculus. We determine the domain and the range of the function first. Next, we check all xy intercepts. We check all asymptotes, vertical, horizontal, and slanted asymptotes, and also we test the function for symmetry. That could be about x-axis, y-axis, or the origin. And finally, we're going to use all the tools in chapter 4, which is about differentiation, involving checking the derivative, the first derivative and the second derivative of the function to determine the critical points and inflection points, and hopefully we determine all relative extrema coming out of the first and the second derivative tests. All right, let's apply all the guidelines to an example. In fact, we have a rational function to start with, and we're going to start with item number 1. We're going to look at the domain and the range of the function. For the domain of the function, we're just checking x's that make this function undefined. Since we have a rational function, whatever makes the bottom 0 should be ruled out. So essentially we are looking at x squared minus 4 equals 0, and that gives you plus or minus 2, which implies that we have all x's in the domain except plus or minus 2. And for that reason, the domain is all x's except plus or minus 2. All right, let's find the range of the function. In fact, there are alternate ways to find the range of a function, but I'm going to use only one way. You can apply it to other functions as well. So you're going to set y equal to the expression of the function here. And I'm going to solve this equation for x. For that reason, I need to multiply both sides of the equation by the bottom of the rational function. So it's going to be y x squared minus 4y equals 2x squared minus 18. Now I'm going to subtract 2x squared from both sides of the equation. And as well, I'm going to add 4y to both sides of the equation so that I can isolate x squared on the left because I can factor that out. And in turn, x squared turns out to be 4y minus 18 divided by y minus 2. And we should take the square root of both sides. So x should be plus or minus radical of 4y minus 18 divided by y minus 2. So we know that for this function to be defined, first off, the bottom of this expression is not going to be 0, so y cannot be equal to 2. Let me just write it here. Also, this expression here has to be positive. So now you go ahead, pause the video, you go ahead and look at two cases. In one case, you're going to check 4y minus 18 positive, y minus 2 positive, so that the ratio is going to be positive. And in the second case, you're going to check 4y minus 18 is negative, and y minus 2 is negative. And once you do all, please pause the video and do it. Once you do all, let's see what you have. We have y to be less than 2 or greater than or equal to 9/2. Please check this by yourself. And therefore, the range is going to be the interval negative infinity and 2, both open. And the other one is 9/2 infinity, and 9/2 is included in the domain. All right, the next thing to check is x and y intercepts. So for x-intercepts, all I'm going to do is to solve this equation. 2x squared minus 9 divided by x squared minus 4 equals 0. Those x's solving this equation would be the x-intercept. And if you multiply both sides by the bottom of the rational number, so you're only having 2 times x squared minus 9 equals 0. You can also divide by 2, which is not a big issue here. Okay, so this implies that x's are plus minus 3. When you're asked, by the way, the x and y intercepts, you should show that in the point notation. So essentially, y is 0 for those x's. So one is negative 3, 0, and the other one is 3 and 0. Now let's check the y-intercepts. This time x is going to be 0, so essentially just plug in 0 for x in the expression of the function. So you have negative 18 divided by negative 4, so y is going to be 9/2. So for that reason, in the point notation, you have 0 and 9/2 for the only y-intercept. The next thing in the list is finding asymptotes, if there are any. So let's try to start with vertical asymptotes. We know that since we have a rational function, whatever makes the bottom 0 but not the top would be candidates of vertical asymptotes. And we have x squared minus 4 equals 0, spitting out plus or minus 2. And we know that plus or minus 2 doesn't or do not make the top 0, but just the bottom 0. So you're dividing by 0. So these two numbers, minus 2 and plus 2, are good candidates of vertical asymptotes. So let's analyze the sided limits because that's what we're going to need. Let's start with negative 2. And we're going to list the functions here. And the way we look at it is essentially you just draw a line here. So here is negative 2. If you are on the left of negative 2, you're talking about numbers of the form negative 2, 0.000, maybe 1. Okay. And if you're on the right of negative 2, you are talking about negative 0.9999 all the way. Okay. So all we're going to do is to check the sign of infinity in both cases. So we have x squared minus 4 here. And let's say like we're on the left of -2, so we have numbers of the form -2.0001. So once you square that, that's going to be a number bigger than 4. So 4 minus that 4 in the bottom is going to be positive, so this is positive. But the top is going to be negative, okay? And this implies that you're dividing a negative number by a number which is very close to 0 and positive, so this should be negative infinity, okay? And now let's look at this one. So we are on the right of -2. We're talking about the numbers of the form -1.999. And the square of that for sure is going to be less than 4. So that number minus 4 is going to be negative. So this part is in negative. And the top is still negative. You can check that. So negative dividing negative is going to take us all the way to infinity. So we're going to need those limits to determine the behavior of the function on the left and on the right of the vertical asymptote. And the next thing to determine is the limits for the other candidate for the vertical asymptote. That is in fact +2. Here we go. We still have the left and right limits. So we're going to have 2 here. And on the left, let's choose a sample point. So 1.9999. And on the right, our sample point is 2.00.1. Okay. So again, we're going to just test those numbers. So for this one, we're on the left of 2. So we have numbers of the form 1.999. So it's going to make this number negative. Okay. And this number as well, negative. So the whole thing is going to be plus infinity. And if you're on the right of 2, so you have 2.0001, so that the square of that minus 4 is going to be positive. However, the top is still negative, so this will be negative infinity. All right, so now we have vertical asymptotes, x equals -2 and 2. Let's check for horizontal asymptotes. And we're going to look at the end behavior of the function, which essentially means that we're going to check 2 limits, one at -infinity of the same function, and the other one is the limit at +infinity. And the good news is that we have a rational function. The top is a quadratic, the bottom is a quadratic. Both come with degree 2. So both limits would be the ratio of the leading coefficients. I have at the top 2x squared minus 18, so the leading coefficient is 2 because the leading term is x squared. So here 2, and then in the bottom you have x squared minus 4. The leading term is x squared, the highest order term. So here we go. So the coefficient of that is 1. So both limits would be equal to 2, and this implies that y equals 2 is a horizontal asymptote. Here we go. If you wrap up everything, we have 2 vertical asymptotes, 1 horizontal asymptote, and there is no slanted asymptote. And the next thing in the list is the symmetry of the graph of f. And here we go. Let's test for the symmetry. For x-axis symmetry, what we're going to do is to replace x by x and y by -y in the expression of the function. And call this one to be y, by the way, to start with. And if the function's expression does not change with this type of change of variables, then you can go ahead and call that you have that kind of symmetry. Or if you change x by -x and y by -y, and if y by y, I'm sorry, and if the function's expression doesn't change, you have this symmetry about y-axis. And finally, if you change x to -x and y to -y, so both variables are changed, then if the function's expression doesn't change, that means you have the symmetry about the origin. So let's try the first one real quick. So I'm going to replace y by -y, and I'm going to keep x as is. And this implies that y equals -2x squared minus 9 divided by x squared minus 4, and this is not the same function I started with because this is the negative version of that, so I can immediately rule out that there is no x-axis symmetry. And let's look at x replaced by -x and y replaced by y. So here we go, y equals 2 - x squared, that's quantity squared by the way, minus 9, negative x quantity squared minus 4. This implies that you have 2x squared minus 9, x squared minus 4. It's the exact same expression we start with for function y. So we do have the symmetry about y-axis for sure. And finally, if you replace this is for sort of like something that you should work on, and I'm just telling you that there is no symmetry about the origin. Please pause the video and check that by yourself, please. So in total, we have only the symmetry with respect to y-axis. Next, let's check the first derivative of the function. Here we go. So we're looking at f prime, which essentially means that we're going to use the quotient rule because we have a quotient. So the quotient rule goes like this. We take the derivative of the top, which is just 4x, and we multiply it by the bottom. Okay. And minus, we take the derivative of the bottom, which is 2x, and multiply it by the top. Let's simplify the top. It's 2x squared minus 18. And we divide it by the square of the bottom, which is x squared minus 4 quantity squared. So my task now is to simplify the top, not the bottom, because the bottom is in the compact form, but not the top. So we should work on the top. All right, so this implies that once these guys are canceled out, we have 20x dividing x squared minus 4 quantity squared. Now we have f prime, so why don't we go ahead and find f double prime, and we're going to apply the same idea. We're going to use the quotient rule. So the derivative of the top is 20 and times the bottom minus the top times the derivative of the bottom. And we're going to use the power rule, generalized power rule for differentiation for this. So 2 down, we subtract 1 from the power, which makes it x squared minus 4. And we multiply this by the derivative of the inner part, which is simply 2x. And we square the bottom. And when you square it, the power becomes simply 4 here. So now I'm going to simplify the top, and I'm going to factor out x squared minus 4. So you have 20x squared minus 80. And then I do have, let's see, 40x and 80x squared. All dividing x squared minus 4 to the power of 4. And you can simplify the top further, but let me just show you what I got so far. So this is the first derivative, and this is the second derivative simplified, because once you simplify it, you will see that you will have one of the factors canceled out, because here, as you see that x squared minus 4 is a common factor, so I can cancel one of these powers, so the bottom becomes cubed, and then you can factor out the constant in the other side, like negative 20 in the top, right? So that you have the final expression of f double prime here. Now let's find the critical numbers, and we're looking at the first derivative for that purpose. So we have two kinds essentially. One kind is the one that makes f prime 0, and the other kind is the one making f prime not defined. Okay. Well, first off, negative 2 and plus 2 are making f prime undefined, but we know that negative 2 and plus 2 are not in the domain. In fact, these are vertical asymptotes, so we rule those out since, again, these are not in the domain. So we're just staring at the x's that make f prime 0, and there's only one that makes the top 0, right? So that's, in fact, x equals 0. So this implies that we have only one critical number. That's the kind, again, that makes f prime equals 0. And next is to determine inflection points, if there is any. So there's only one way to do that. We're going to set f double prime to 0. And if you look at this expression, if you're looking for x's that make f double prime 0, and these are the ones making the top 0 only, but this is a positive number multiplying a negative number, there's no way to make this expression 0. So in fact, this is not equal to 0. For that reason, there is no inflection point. And here we go, we do not have any kind of inflection point, and the only critical point or number is x equals 0. So now it's time to choose intervals for testing the function for increasing, decreasing, or concavity. So we have two vertical asymptotes, so these are going to be the ones getting into the table as well as the critical number. For that reason, we have 4 test intervals. One is negative infinity and negative 2. Negative 2 and 0, remember 0 is a critical number, and 0 to 2, the next vertical asymptote, and 2 to infinity. And at this moment, you can pause the video and evaluate f prime and f double prime at those points. But first, obviously, we check the sign of f prime to determine the increasing, decreasing behavior. So apparently with the test values you pick from this interval, f prime turns out to be negative. And from here, you pick a test number like -1 and feed it back into f prime, and turns out that you have f prime and negative. And for the other two intervals, they are positive. So we know that f is decreasing here, increasing here, and increasing also in the last interval. And we also look at f double prime in terms of its sign and in the same intervals. So f double prime here is negative. That implies that we have concave downward type graph. And here, as you see, that f double prime is positive. So that's why we have concave upward type graph. And in the last interval, f double prime is a negative, so we have concave downward. To be specific, so how do you sort of like combine each row here? Like you have two different behaviors, like decreasing and concave downward. So what is the exact graph of the function in this interval? So concave down is something like this, obviously, and the piece that is decreasing is this one. So for this interval, the graph of the function looks like the right-hand side of the concave downward. Or if you have an increasing concave downward behavior, so concave downward and increasing means like you're just considering this type of piece to see the behavior of the function for that sub-interval. Since there's only one critical number, which is x equals 0, you can apply the second derivative test to check the sign of f double prime at 0, and it turns out to be plus, so which essentially means by the second derivative test that we have a relative minimum at x equals 0. And finally, we graph the function to be able to understand the behavior. So you can take your x min to be -10 and plus 10 for the x max. You will see that you will have all the crucial parts of the graph getting into the viewing frame in your calculator. So you have a vertical asymptote here, you have a vertical asymptote here, you have a horizontal asymptote here. So you have a decreasing behavior all the way starting from -infinity to by -2, and then you have between -2 and 2, you have a decreasing piece and increasing piece, and it's all concave upward type graph. And on the right, starting from -infinity again, this is in fact increasing all the way tangentially to horizontal asymptote. It doesn't touch that at all. Okay, so in fact, this tells us all the important behavior of the function, including the relative extrema, which is happening right here at the critical point, because we know that x equals 0 is a critical point, and we just showed that in the table. we have a relative minimum value happening over there, and that is in fact 9/2, and there's no relative max as you see on the graph of the function. And as you see, that graphing takes time. It requires rigorous analysis. You check the first derivative and the second derivative, and you check asymptotes and everything else to be able to see the full picture in the graph so that you graph the function in a very educated way. I'm going to close this video with a comment about slant asymptotes. So we never had a chance to talk about slant asymptotes because the function that we dealt with didn't have any slant asymptote. So slant asymptotes happen for rational functions when you have the degree of the top greater than the degree of the bottom. And this is a good example of that. So you have a quadratic dividing a linear polynomial, and the degree of the top is 2, the degree of the bottom is 1. So it's likely that you're going to have a slant asymptote, and to be able to catch that, you need to have a long division. So after the long division, as you see that you have x popping here, and then 4/x minus 2 is popping here as well. So this implies that this term, not the rational function left over, but this term here is exactly what the slant asymptote is, and we call that y equals x here is a slant asymptote for the graph of f. And the question is like, how does the slant asymptote look like if you look at the graph of the function? Here we go. Slant asymptote is essentially slanted, as you see, slanted line. And you have y equals x here. So as you see that, the graph of f goes to infinity along y equals x line. And similarly, the graph of f goes to negative infinity along the same line. That's exactly what slant asymptote means. All right, it's time for practice. So why don't you go ahead and start the recitation videos, and you have one example where you have a rational function where the degree of the top is exactly the same as the degree of the bottom. So watch this video because I put all the details from scratch, from finding the domain range, symmetry, asymptotes, to using the first, second derivative tests to find relative extrema, inflection points, critical points, and on and on and on. And in the second exercise, you're going to have another rational function. I want you to pay attention to this problem particularly because the degree of the top is greater than the degree of the bottom. This is where you have the slant asymptote. So please go ahead and check this problem out. And then finally, I put a non-trivial example that uses a transcendental function, as you see, of x minus 1 and ln, natural log of x minus 1. So please check this example out as well because we never had one in the lecture notes like this. All right, we had only one objective today, which is analyzing and sketching the graphs of functions. I think we successfully accomplished that, and I'll see you in another video. Bye.